You're 35,000 feet up. Seatbelt sign pings off. You lean over to the window, ready for that glorious view of clouds and mountains and tiny little cars, and that's when you spot it. Right at the bottom of the window, a tiny hole. Your brain does the thing. Wait, is that supposed to be there? Relax. Not only is it supposed to be there, it's one of the cleverest bits of engineering you've ever looked straight past. What you're actually looking at is a triple-layered sandwich of very deliberate engineering paranoia. The outer pane, that's the strong one. It carries the full force of the pressure difference between the cabin and the near vacuum outside. The middle pane? That's the backup. It's not supposed to take the main load. But if the outer pane ever failed, which is extraordinarily rare, the middle pane steps up like an understudy who's been quietly memorizing every line since day one. And the inner pane, the one you're currently pressing your nose against, that's essentially a scratch protector. It exists so you can treat it like a bus window. 3 layers, 2 air gaps, 1 very deliberate tiny hole. The pressure out there is so low that your lungs simply can't extract oxygen. Meanwhile, inside the cabin, the aircraft is maintaining air pressure roughly equivalent to standing on a mountain about 200–400 meters high. The fuselage is essentially a pressurized aluminium balloon. Here's a way to picture it. Blow up a balloon. The rubber is stretched tight because the pressure inside is higher than outside. Now replace rubber with aircraft-grade aluminium. Party balloon with 400-ton jet. Every single flight, that fuselage expands slightly under pressure and then contracts when you land. Engineers call each pressurization cycle a cycle, but every cycle accumulates microscopic wear, and all of that pressure, it's trying to push through your window. This is where the tiny hole earns its keep. It's called the bleed hole, sometimes the breather hole. It sits at the very bottom of the middle pane, and it's about 1 millimeter wide, the diameter of a pinhead, and yet this tiny opening is doing 2 jobs at exactly the same time. Job 1, it allows air to flow between the cabin and the gap between the outer and middle panes. This equalizes the pressure on both sides of the outer pane so the window experiences the same force inside and out. Without this, the outer pane would bulge inward under the pressure difference, like a balloon squeezed from one side. Over time, that causes stress fractures. Job 2, because air is constantly flowing through that hole, moisture is being continuously wicked away from the gap. No condensation, no fogging, no frost creeping across the space between the panes mid-flight. 1 millimeter, 2 jobs. Warm, humid cabin air meets the cold outer window pane. If there's nowhere for the resulting moisture to go, no bleed hole to let it escape, it collects between the panes. Fog, then frost, then permanently cloudy, irreversibly ruined window glass. Before bleed holes became standard, mid-flight window fogging was a known, frustrating, very real problem. And the solution ties into a much larger, much more serious lesson. One that aviation learned the very hard way. In 1952, the de Havilland Comet became the world's first commercial jet airliner. It had large, elegant windows, square windows, and the square, that shape we find absolutely everywhere, was silently tearing the planes apart. Here's the physics. When you cut any hole in a pressurized metal structure, the stress that would normally flow through the surrounding material has to detour around the opening. With a circular hole, that stress flows smoothly around the curve, like a river bending gently around a rock. With a square hole, the stress reaches a corner, a sharp right angle, and has nowhere to go. It piles up. Engineers call this a stress concentration. And in a fuselage that's being pressurized and depressurized on every single flight, those corners become failure points. By 1954, 2 comets had broken apart mid-flight. Investigators rebuilt entire sections of fuselage and pressurized them underwater to watch exactly where the cracks formed. And they traced every failure to the same place, the corners of the square windows. The fix was almost embarrassingly simple. Make them round. A circle has no corners. No corners means no stress concentration points. The force flows evenly all the way around. No single point is carrying more load than any other. It's the same reason arches have held up bridges and cathedrals for thousands of years. The curve distributes the load, so your airplane window is round for a reason written in tragedy. And the next time you settle into your seat, look at your window, find the hole, smile to yourself. You're armed with genuine engineering knowledge, a faint sense of historical tragedy, and absolutely nobody asked for any of it. Safe travels.